Next we will see the isomerism in coordination compounds. Unlike the isomerism which you studied in class 11, here also we are having the structural isomerism and stereoisomerism. Alright, the structural isomerism is not divided into chain, positional, functional, metamers, no. Here in case of structural isomerism, you will be having ionization isomerism, then you will be having hydrate isomerism, you will be having linkage isomerism, then you will be having coordinate isomerism, and you will be having that is ligand isomerism. Alright. Now in stereoisomerism, it is same thing, that is you are having geometrical isomerism and optical isomerism. Geometrical isomers is what you can say divisible into cis and trans, are of two types, and optical is again dextro and levo, so to say. So first we will see ionization isomerism. In case of structural isomerism, the first one is ionization isomerism. As I said you, isomerism is structural and stereo, we can say that. So structural isomerism, the first one is your ionization isomerism. So what is ionization isomerism? If you simplify the name, you can come to know. Alright, that is what I mean to say. That means you will be having two ions, two different ions. Molecular formula will be the same, but the ions will be different. Ions means what ions? Complex ion and simple ion. Alright, complex ion and simple ion will be different. From here itself, from the name itself, you can guess something, that what I mean to say. Alright, in this way only you can make the things very simple in chemistry. Alright, from the name itself. Now, what is ionization isomerism? You see the definition. When coordination compounds having the same molecular formula show a difference in their ionization behavior. When coordination compounds having the same molecular formula shows a difference in their ionization behavior and furnish different types of ions in solution, the phenomena is called ionization isomerism. Alright, as I said you already, that the ions will be different. That is, simple ions and the counter ions will be different, but the molecular formula will be the same. Alright, so they furnish different types of ions in solution, we can say that. Clear? And that phenomena, that particular process is called as ionization isomerism. Again I repeat, the molecular formula will be the same, but the structural formula will be such that they will produce different ions in solution, we can say that. Clear? Now let us take the example of this, that is CO Br NH3 whole 5 SO4. Alright, so you got this one particular compound is this. Now you can have it in this way also. You can write in this way also, CO NH3 whole 5 SO4 and Br. What is differing here? Here the complex ion is this, and the counter ion or simple ion is sulfate ions. Here the complex ion is this, you can see, and the counter ions is your Br. How do we come to know? It will dissociate. Suppose it will dissociate. I said it will produce different ions in solution. So in the aqueous solution state, this compound will give you what? This compound will give you SO4 2 minus, SO4 2 minus plus CO Br NH3 whole 5. Alright, that is 2 plus. You can say that. See here. Now here this compound will give you Br minus, and this will give you CO NH3 whole 5 SO4 plus. Alright. So in this way, what you find is that here in this particular case, you can see that here we are having the bromide ion as a simple ion, and here we are having sulfate ion as sulfate ions. What you can say, simple ion, we can say that. How will you distinguish? When you dissolve in water, it dissociates into these ions. Is the ions visible to us? How will you come to know that they produce different ions in solution? Very simple. You go for a test, an analytical test. What you do is that you take barium chloride solution. You add 2 drops of barium chloride solution to these two, what you can say, substances, these two solutions. Alright, you take these two solutions in 2 test tubes and you drop barium chloride solution to each. This will give you white PPT. Alright, this will give you white PPT because barium sulfate will be found. Correct, it will give you white PPT, but this will not give you white PPT. Alright, so in this way, that is the formation of that is white PPT proves that this particular one produces the sulfide ions and this produces other than the sulfide ions, that is a bromide ion, we are getting it. Okay. Now next is if you can also take AgNO3 solution. You add AgNO3 solution to either of this particular test tubes. I said, you take in this in test tube 1, this one in test tube 2, you add AgNO3 solution. Now this will give you a yellow PPT of AgBr. AgNO3 will react with the Br minus ion to give a yellow PPT of AgBr. This will not give you any particular PPT, we can say that. So you can do with AgNO3 solution also. You can do with barium chloride solution also. It's up to you. Alright. So in this way, what you find is that is these two tests clearly distinguishes that it produces different ions in solution. Moreover, this particular substance will be red-violet in color and this will be pure red in color. We can say that. That means this is more of that is a reddish violet and this is completely red in color. From there also we can distinguish it. That these two substances are different even if the molecular formula is the same. Yes, molecular formula is the same. COBrNH3 whole 5SO4. Here also COBrNH3 whole 5SO4. Same thing. Only the ions is different. Alright, in aqueous solution. So for that purpose, this particular substance shows that is ionization isomerism. Alright, and ionization isomers, and the phenomena is known as ionization isomerism. We can say that. Alright, when it produces different types of ions in solution. Now, the next is the second one is your hydrate isomerism. Hydrate. The second one. Hydrate isomerism. Again, from the name itself, we can say hydrate. So the water molecules is going to differ. The molecular formula will be the same, but the water molecules is going to differ because hydrate has come from the word water. Hydrate. Alright, clear. So the water molecules can act both as ligands as well as simple molecules of water oxidation. Alright. The water molecules can act both as ligands as well as simple molecule of water of crystallization. Alright. When two complexes differ in this aspect, alright, it is called as hydrate isomerism. What I said water molecule can act as ligand also. Water molecule can act as water oxidation also. So when two complexes, molecular formula will be the same, but when two complexes differ in this particular aspect, that means in one of the complex water molecule acts as a ligand, in one of the complex water molecule acts as a water of crystallization. Then this particular isomer is called as hydrate isomer and the phenomena is known as hydrate isomerism, so to say. Alright, in this way we can say. So let us have some examples so that we will come to know. Now see here, we can have CrH2O whole 6 Cl3. Now here the water molecule acts as a ligand, you can say that. It's a ligand. Now I can write it in this way also. CrH2O whole 5 Cl, then Cl2 dot water. One water molecule, I took it outside. So when I took it outside, it acts as a water of crystallization. The molecular formula remains the same. We can say that. Clear? Same. Here also 3Cl, here also 3Cl, here 6 water, here also 6 water and 1 chromium. Got it? You can also write in this way. One more also you can write. What is that? That is CrH2O whole 4 Cl2. Then how many Cl will remain? Out of 3 Cl, that is 1 Cl remains, and 4 out of 6 H2O, 4 H2O has come. So 2 H2O is there. So 2 H2O. See here 2 molecules of water oxidation, we are getting it. Alright. So water molecule can act as ligand as well as it acts as water oxidation. So when the water molecule acts as both as ligand as well as water oxidation, and in this aspect only it is differing. Alright, the phenomena is called as the compound is called as hydrate isomers and the phenomena is known as hydrate isomerism. Now what you can see is that how will you differentiate it? Now this particular compound will be violet in color on the basis of color, and this particular compound will be blue-green, you can say that, and this particular compound will be more of green color, we can say that, dark green color. Alright, so the color is going to differ. About the color, I will tell you in CFT that how we determine the color. of a particular coordination compounds also that. Alright, I'll tell you in CFT. CFT is crystal field theory. So now just to remember it, this will be violet, this will be blue-green, and this will be dark green in color, so to say. And the color differs on the basis of the number of water flagellation. Alright, on the basis of here one water molecule, so it is blue-green. Here there is 2 water molecules, so it becomes more of green in color, we can say that. Clear? In this way, that is when the water molecule can act both as ligand as well as water flagellation, then it is known as hydrate isomers, and the phenomena is known as hydrate isomerism. Next, after that we will be having the linkage isomerism. What is that I said? Linkage. Linkage isomerism. Answer that. So, the third one is your linkage. Now, this is also called as structural salt isomerism. Structural salt isomerism. Either linkage we can say, or we can say structural salt isomerism. Now, what is again from the name? Linkage. Linkage with what? With the central atom. Alright, the ligands which is attached to the central atom, that is going to differ. Alright, so there will be some, what you can say, change in the ligands, we can say that. That will be the linkage. That is the link, we can say that. Now, the isomerism arises when the ligands have 2 different atoms available for coordination with the central metal atom. When the ligands have 2 different atoms available for coordination with the central metal atom. That means I am talking to you in one word, I am talking to you with ambident ligands. Because in case of ambident ligands, there are 2 donor atoms. Ambident ligand means, for example, NO2 and ONO. In case of NO2, nitrogen is a donor atom. In case of ONO, oxygen is a donor atom. In case of CNS, sulfur is a donor atom. In case of NCS, nitrogen is a donor atom. So in this way, when a particular ligand has got 2 donor atoms for coordination with the central metal atom, we can say that we are having an ambident ligands. In one isomer, one donor atom, acts as a ligand, or it acts as a donor atom to one of the central metal atom. In other, what you can say, isomer, another donor atom, another donor atoms gives the lone pair of electrons to the central metal atom. So what I said you, again I repeat the definition just to explain to this one. The isomerism arises when the ligands have 2 different donor atoms for coordination with a central metal ion, we can say that. And hence the phenomena is known as ligand isomerism, or it is called as structural salt, ligand, what you can say, the phenomena is called as linkage isomerism, or the structural salt isomerism, so to say. Alright, again I repeat, here what you find is that the ligand is ambident. So in one of the isomer, one particular atom, for example, suppose NO2 and ONO is there. So in one isomer, nitrogen acts as a donor atom with a central metal atom. So nitrogen, what you can say, gives the lone pair of electrons to the central metal atom. So there is a coordination between nitrogen and the central metal atom. In another isomer, oxygen is a donor atom. Oxygen is a linkage, we can say that, with the central metal atom and that of the ligand, so to say. So this is possible only when the ligands are ambident in nature, we can say that, when it has got 2 donor atoms. Now let me give an example to you, then it will be clear to you. Let me give an example. So see, for example, we are having here, that is CO and what I said you, let us say NO2. So others we can have it like here 1, 2, 3, 4, 5. One more we can say, that is ammonia. Let us see. Other ligands are ammonia, NH3. So the formula will be CO, that is cobalt, NH3 1, 2, 3, 4, 5, NH3 whole 5, NO2. Alright, that is CO, NH3 whole 5, NO2, and it will be how many? Let us calculate also the oxidation number. NH3 is neutral, 0. Alright, now cobalt, what you can say, it is 3 plus. So NO2 is minus 1. So plus 3 minus 1, it will be what? Plus 2. Very simple maths. Alright. Now next is that is here CO. Here it is NH3. Here one more NH3. Here it is one more NH3. Here it is NH3. 1, 2, 3, 4. Another NH3. And NO2 now, already I said you, it will be ONO. Same thing, it will be 2 plus. So here you see what is the difference here? The difference is here. Here nitrogen is a donor atom, which is a linkage with the central metal atom. Here oxygen is a linkage with the central metal atom. Oxygen is a donor atom. Alright, that is known as linkage or structural salt isomerism. So to say, we can say that. I think it's clear. Alright, one example I'm giving you, I think it's clear. Now the next one is your coordination isomerism. Coordination isomerism. Coordination. Now from here also same thing, we can say coordination means the coordination complexes is going to differ. Alright. So let us see, this type of isomerism is shown by complexes. Alright. First of all, this type of isomerism is shown by, which I said you, complexes, in which the positive and the negative parts are the complex species. In which the positive as well as the negative part of the complex species. Alright. Till now, we were doing, alright, for example, in this particular compound, here's what I said you, CONH3 whole 5 within bracket NO2, we can say that, plus 2 plus. So here we are having a simple ion when here we are having a complex ion. We are having a simple ion and a complex ion. Here both, what you can say, the positive and the negative are the complex ion. Alright, here we are having a simple ion and a complex ion. So complex ion is, let it be positive, so simple ion will be negative. Or what you can say, the complex ion is negative and the simple ion is positive, it depends. But here, in case of, listen carefully, in case of coordination isomerism, both the parts, that is the positive and the negative parts, both are complex in nature. I said you already, the coordination complex is going to differ. Alright, so the isomerism arises due to the interchange of ligands between the coordination spheres of the positive and the negative parts. Again I repeat, the isomerism arises due to the interchange of ligands between the positive and negative parts of the coordination spheres. Alright, so what you find is that there is interchange of ligands between the coordination spheres of the positive and the negative parts. So this isomerism arises. I said you already, again I repeat, both the positive and negative parts are the complex ions. Alright, now let me tell you what is that. So for example, we are having here, that is example, let me rub it first. I will not have space. Yeah. Let me rub it. Okay, fine. Now we can have it here. That is an example we can take, like what I should say, CONH3 whole 4. Alright, 1. This is the positive, and first always we write the positive, and this is here PtCl4. Alright, so we got one complex is that CONH3 whole 4 PtCl4. Now what is going to happen here? That is just interchange of the positive and negative parts. So what it will be? PtNH3 whole 4, and here it will be CO, that is Cl4. That's it. So in this way, this particular one, it acts as, we can say, a ligand, we can say that. That is, it's known as coordination isomerism. It acts as a ligand, so the ligands is differing here, we can say that. So instead of cobalt, you can also take here copper. That also can be done. Here also copper it will be. That also can be possible. Alright. So hence cobalt, copper, anything you can take it here. Got it? But that it should exist. The compound should exist. That is what I mean to say. Clear? So in this way, here this particular isomerism is called as coordination isomerism. Next is the last one is your ligand isomerism. Ligand isomerism. Same thing, from the name itself we can come to know, like the coordination complexes was differing. See, it is differing. Coordination complexes. Here in case of ligand isomerism, the ligands attached to it is going to differ. Alright. So this type of isomerism arises when the ligand present in the complex exists in 2 or more isomeric form. Alright. 2 or more isomeric form. Alright, again I repeat, this type of isomerism arises when the ligand present in the complex can exist in two or more isomeric form, or more than one isomeric form, we can say that. Clear? So that is called as ligand isomerism. Now, example we can give it, it is nothing but we can write like CO, let me write COPN Cl2 positive charge, we can say that. We can have this one as COTN Cl2 and positive charge. Got it? Now, so we can say COPN, more than one. It should be. Sorry, I forgot to write this. More than once. It should be. So PN and TN. What are this? What is this PN and TN? We have never heard of this particular one. PN is 1,2-diaminopropane. Alright, and TN is 1,3-diaminopropane. Alright, what I said? PN is 1,2-diaminopropane. See, amino 1, 2. Here that is CH3. Here it will be CH. Here it will be CH2. This is 1,2-diaminopropane. And TN is 1,3-diaminopropane. 1, 3. Alright, this is NH2. This is your CH2. This is CH2, this is CH2. This is 1,3-diaminopropane, this is 1,2-diaminopropane. We can say that. Alright, so what is differing here? The ligand is differing. This is 1, 2, this is 1, 3. The position of the amino group is differing. So hence it is called as ligand isomerism because the ligand differs. So we can say that. So this is your PN and this is your TN. In short, we have written the abbreviated form. You know, the several abbreviated forms I have said you earlier also. So in this way, this is coming under the, so to say, that is ligand isomerism. Now again same thing, how did I get the plus charge, you may ask me. Cobalt is 3+, I said you in the previous example. Now PN it is and TN, both are neutral in nature. Cl2 is -1. So my 2Cl is -2. So +3 -2 will be what? +1. Here also same thing, +3 -2 will be +1. In this way. So we come under that is ligand isomerism. So we have discussed with you that is your ionization isomerism, we have discussed hydrate isomerism, we have discussed linkage or structural result isomerism, we have discussed coordination isomerism, and we have discussed that is ligand isomerism. Okay, thank you.